The noble gases make a group of chemical elements with similar properties. Under standard conditions, they are all odorless, colorless, monatomic gases with very low chemical reactivity. The 6 noble gases that occur naturally are helium, neon, argon, krypton, xenon, and the radioactive radon. For the first 6 periods of the periodic table, the noble gases are exactly the members of group 18 of the periodic table. It is possible that due to relativistic effects, the group 14 element flerovium exhibits some noble gas-like properties, instead of the group 18 element unoxium. Noble gases are typically highly unreactive except when under particular extreme conditions. The inertness of noble gases makes them very suitable in applications where reactions are not wanted. For example, argon is used in light bulbs to prevent the hot tungsten filament from oxidizing. Also, helium is used in breathing gas by deep-sea divers to prevent oxygen and nitrogen toxicity. The properties of the noble gases can be well explained by modern theories of atomic structure. Their outer shell of valence electrons is considered to be full, giving them little tendency to participate in chemical reactions, and it has been possible to prepare only a few hundred noble gas compounds. The melting and boiling points for a given noble gas are close together, differing by less than 10 degrees Celsius, that is, they are liquids over only a small temperature range. Neon, argon, krypton, and xenon are obtained from air in an air separation unit using the methods of liquefaction of gases and fractional distillation. Helium is sourced from natural gas fields which have high concentrations of helium in the natural gas, using cryogenic gas separation techniques. And radon is usually isolated from the radioactive decay of dissolved radium, thorium, or uranium compounds. Noble gases have several important applications in industries such as lighting, welding, and space exploration. A helium-oxygen breathing gas is often used by deep-sea divers at depths of seawater over 55 meters to keep the diver from experiencing oxygen toxemia, the lethal effect of high-pressure oxygen and nitrogen narcosis. The distracting narcotic effect of the nitrogen in air beyond this partial pressure threshold. After the risks caused by the flammability of hydrogen became apparent, it was replaced with helium in blimps and balloons. History. Noble gas is translated from the German noun Edelgas, first used in 1898 by Hugo Erdmann to indicate their extremely low level of reactivity. The name makes an analogy to the term noble metals, which also have low reactivity. The noble gases have also been referred to as inert gases, but this label is deprecated as many noble gas compounds are now known. Rare gases is another term that was used, but this is also inaccurate because argon forms a fairly considerable part of the Earth's atmosphere due to decay of radioactive potassium-40. Pierre Janssen and Joseph Norman Lockyer discovered a new element on August 18, 1868 while looking at the chromosphere of the Sun, and named it helium after the Greek word for the Sun, eta lambda iota omicron sigma. No chemical analysis was possible at the time, but helium was later found to be a noble gas. Before them, in 1784, the English chemist and physicist Henry Cavendish had discovered that air contains a small proportion of a substance less reactive than nitrogen. A century later, in 1895, Lord Rayleigh discovered that samples of nitrogen from the air were of a different density than nitrogen resulting from chemical reactions. Along with Scottish scientist William Ramsay at University College, London, Lord Rayleigh theorized that the nitrogen extracted from air was mixed with another gas, leading to an experiment that successfully isolated a new element, argon, from the Greek word alpha rho gamma omicron sigma. With this discovery, they realized an entire class of gases was missing from the periodic table. During his search for argon, Ramsay also managed to isolate helium for the first time while heating cleverite, a mineral. In 1902, having accepted the evidence for the elements helium and argon, Dmitry Mendeleev included these noble gases as group 0 in his arrangement of the elements, which would later become the periodic table. Ramsay continued to search for these gases using the method of fractional distillation to separate liquid air into several components. In 1898, he discovered the elements krypton, neon, and xenon, and named them after the Greek words kappa rho upsilon pi tau omicron sigma, nu epsilon omicron sigma, and xi epsilon nu omicron sigma, respectively. Radon was first identified in 1898 by Friedrich Ernst Dorn, and was named radium emanation, but was not considered a noble gas until 1904 when its characteristics were found to be similar to those of other noble gases. Rayleigh and Ramsay received the 1904 Nobel Prizes in Physics and in Chemistry, respectively, for their discovery of the noble gases. In the words of J. E. Cederblom, then president of the Royal Swedish Academy of Sciences, the discovery of an entirely new group of elements, of which no single representative had been known with any certainty, is something utterly unique in the history of chemistry, being intrinsically an advance in science of peculiar significance. The discovery of the noble gases aided in the development of a general understanding of atomic structure. In 1895, French chemist Henri Moissan attempted to form a reaction between fluorine, the most electronegative element, and argon, one of the noble gases, but failed. Scientists were unable to prepare compounds of argon until the end of the 20th century. But these attempts helped to develop new theories of atomic structure. Learning from these experiments, Danish physicist Niels Bohr proposed in 1913 that the electrons in atoms are arranged in shells surrounding the nucleus, and that for all noble gases except helium the outermost shell always contains 8 electrons. In 1916, Gilbert N. Lewis formulated the octet rule, which concluded an octet of electrons in the outer shell was the most stable arrangement for any atom. This arrangement caused them to be unreactive with other elements since they did not require any more electrons to complete their outer shell. In 1962, Neil Bartlett discovered the first chemical compound of a noble gas, xenon hexafluoroplatinate. Compounds of other noble gases were discovered soon after. In 1962 for radon, radon difluoride, and in 1963 for krypton, krypton difluoride. The first stable compound of argon was reported in 2000 when argon fluorohydride was formed at a temperature of 40 K. In December 1998, scientists at the Joint Institute for Nuclear Research working in Dubna, Russia bombarded plutonium with calcium to produce a single atom of element 114, flerovium. Preliminary chemistry experiments have indicated this element may be the first superheavy element to show abnormal noble gas-like properties, even though it is a member of Group 14 on the periodic table. In October 2006, scientists from the Joint Institute for Nuclear Research and Lawrence Livermore National Laboratory successfully created synthetically unoxium, the seventh element in Group 18, by bombarding californium with calcium. Physical and atomic properties. For more data, see noble gas. The noble gases have weak interatomic force, and consequently have very low melting and boiling points. They are all monatomic gases under standard conditions, including the elements with larger atomic masses than many normally solid elements. Helium has several unique qualities when compared with other elements. Its boiling and melting points are lower than those of any other known substance. It is the only element known to exhibit superfluidity. It is the only element that cannot be solidified by cooling under standard conditions. A pressure of 25 standard atmospheres must be applied at a temperature of 0.95 K to convert it to a solid. The noble gases up to xenon have multiple stable isotopes. Radon has no stable isotopes. Its longest-lived isotope, 222 Rn, has a half-life of 3.8 days and decays to form helium and polonium, which ultimately decays to lead. Melting and boiling points generally increase going down the group. The noble gas atoms, like atoms in most groups, increase steadily in atomic radius from one period to the next due to the increasing number of electrons. The size of the atom is related to several properties. For example, the ionization potential decreases with an increasing radius because the valence electrons in the larger noble gases are farther away from the nucleus and are therefore not held as tightly together by the atom. Noble gases have the largest ionization potential among the elements of each period, which reflects the stability of their electron configuration and is related to their relative lack of chemical reactivity. Some of the heavier noble gases, however, have ionization potentials small enough to be comparable to those of other elements in molecules. It was the insight that xenon has an ionization potential similar to that of the oxygen molecule that led Bartlett to attempt oxidizing xenon using platinum hexafluoride, an oxidizing agent known to be strong enough to react with oxygen. Noble gases cannot accept an electron to form stable anions, that is, they have a negative electron affinity. The macroscopic physical properties of the noble gases are dominated by the weak van der Waals forces between the atoms. The attractive force increases with the size of the atom as a result of the increase in polarizability and the decrease in ionization potential. This results in systematic group trends. As one goes down group 18, the atomic radius, and with it the interatomic forces, increases, resulting in an increasing melting point, boiling point, enthalpy of vaporization, and solubility. The increase in density is due to the increase in atomic mass. The noble gases are nearly ideal gases under standard conditions, but their deviations from the ideal gas law provided important clues for the study of intermolecular interactions. The Leonard-Jones potential, often used to model intermolecular interactions, was deduced in 1924 by John Leonard-Jones from experimental data on argon before the development of quantum mechanics provided the tools for understanding intermolecular forces from first principles. The theoretical analysis of these interactions became tractable because the noble gases are monatomic and the atoms spherical, which means that the interaction between the atoms is independent of direction, or isotropic. Chemical properties. The noble gases are colorless, odorless, tasteless, and non-flammable under standard conditions. They were once labeled group 0 in the periodic table because it was believed they had a valence of 0, meaning their atoms cannot combine with those of other elements to form compounds. However, it was later discovered some do indeed form compounds, causing this label to fall into disuse. Configuration. Like other groups, the members of this family show patterns in its electron configuration, especially the outermost shells, resulting in trends in chemical behavior. The noble gases have full valence electron shells. Valence electrons are the outermost electrons of an atom and are normally the only electrons that participate in chemical bonding. Atoms with full valence electron shells are extremely stable and therefore do not tend to form chemical bonds and have little tendency to gain or lose electrons. However, heavier noble gases such as radon are held less firmly together by electromagnetic force than lighter noble gases such as helium, making it easier to remove outer electrons from heavy noble gases. As a result of a full shell, the noble gases can be used in conjunction with the electron configuration notation to form the noble gas notation. To do this, the nearest noble gas that precedes the element in question is written first, and then the electron configuration is continued from that point forward. For example, the electron notation of phosphorus is 1s2 2s2 2p6 3s2 3p3, while the noble gas notation is Ni 3s2 3p3. This more compact notation makes it easier to identify elements, and is shorter than writing out the full notation of atomic orbitals. compounds. The noble gases show extremely low chemical reactivity, consequently, only a few hundred noble gas compounds have been formed. Neutral compounds in which helium and neon are involved in chemical bonds have not been formed, while xenon, krypton, and argon have shown only minor reactivity. The reactivity follows the order Ni less than He less than R less than Kr less than Xe less than Rn. In 1933, Linus Pauling predicted that the heavier noble gases could form compounds with fluorine and oxygen. He predicted the existence of krypton hexafluoride and xenon hexafluoride, speculated that XeF8 might exist as an unstable compound, and suggested xenic acid could form perxenate salts. These predictions were shown to be generally accurate, except that XeF8 is now thought to be both thermodynamically and kinetically unstable. Xenon compounds are the most numerous of the noble gas compounds that have been formed. Most of them have the xenon atom in the oxidation state of +2, +4, +6, or +8 bonded to highly electronegative atoms such as fluorine or oxygen, as in xenon difluoride, xenon tetrafluoride, xenon hexafluoride, xenon tetroxide, and sodium perxenate. Xenon reacts with fluorine to form numerous xenon fluorides according to the following equations. Xe plus F2 XeF2 Xe plus 2F2 XeF4 Xe plus 3F2 XeF6. Some of these compounds have found use in chemical synthesis as oxidizing agents. XeF2, in particular, is commercially available and can be used as a fluorinating agent. As of 2007, about 500 compounds of xenon bonded to other elements have been identified, including organoxenon compounds, and xenon bonded to nitrogen, chlorine, gold, mercury, and xenon itself. Compounds of xenon bound to boron, hydrogen, bromine, iodine, beryllium, sulfur, titanium, copper, and silver have also been observed, but only at low temperatures in noble gas matrices, or in supersonic noble gas jets. In theory, radon is more reactive than xenon, and therefore should form chemical bonds more easily than xenon does. However, due to the high radioactivity and short half-life of radon isotopes, only a few fluorides and oxides of radon have been formed in practice. Krypton is less reactive than xenon, but several compounds have been reported with krypton in the oxidation state of +2. Krypton difluoride is the most notable and easily characterized. Under extreme conditions, krypton reacts with fluorine to form KrF2 according to the following equation. Kr plus F2 KrF2 compounds in which krypton forms a single bond to nitrogen and oxygen have also been characterized, but are only stable below -60 degrees Celsius and -90 degrees Celsius respectively. Krypton atoms chemically bound to other nonmetals as well as some late transition metals have also been observed, but only either at low temperatures in noble gas matrices, or in supersonic noble gas jets. Similar conditions were used to obtain the first few compounds of argon in 2000, such as argon fluorohydride, and some bound to the late transition metals copper, silver, and gold. As of 2007, no stable neutral molecules involving covalently bound helium or neon are known. The noble gases, including helium, can form stable molecular ions in the gas phase. The simplest is the helium hydride molecular ion, He+, discovered in 1925. Because it is composed of the two most abundant elements in the universe, hydrogen and helium, it is believed to occur naturally in the interstellar medium, although it has not been detected yet. In addition to these ions, there are many known neutral isomers of the noble gases. These are compounds such as ARF and KRF that are stable only when in an excited electronic state. Some of them find application in excimer lasers. In addition to the compounds where a noble gas atom is involved in a covalent bond, noble gases also form non-covalent compounds. The clathrates, first described in 1949, consist of a noble gas atom trapped within cavities of crystal lattices of certain organic and inorganic substances. The essential condition for their formation is that the guest atoms must be of appropriate size to fit in the cavities of the host crystal lattice. For instance, argon, krypton, and xenon form clathrates with hydroquinone, but helium and neon do not because they are too small or insufficiently polarizable to be retained. Neon, argon, krypton, and xenon also form clathrate hydrates, where the noble gas is trapped in ice. Noble gases can form endohedral fullerene compounds, in which the noble gas atom is trapped inside a fullerene molecule. In 1993, it was discovered that when C60, a spherical molecule consisting of 60 carbon atoms, is exposed to noble gases at high pressure, complexes such as He at C60 can be formed. As of 2008, endohedral complexes with helium, neon, argon, krypton, and xenon have been obtained. These compounds have found use in the study of the structure and reactivity of fullerenes by means of the nuclear magnetic resonance of the noble gas atom. Noble gas compounds such as xenon difluoride are considered to be hypervalent because they violate the octet rule. Bonding in such compounds can be explained using a 3-center-4 electron bond model. This model, first proposed in 1951, considers bonding of 3 collinear atoms. For example, bonding in XeF2 is described by a set of 3 molecular orbitals derived from p orbitals on each atom. Bonding results from the combination of a filled p orbital from Xe with 1/2 filled p orbital from each F atom, resulting in a filled bonding orbital, a filled non-bonding orbital, and an empty anti-bonding orbital. The highest occupied molecular orbital is localized on the 2 terminal atoms. This represents a localization of charge which is facilitated by the high electronegativity of fluorine. The chemistry of heavier noble gases, krypton and xenon, are well established. The chemistry of the lighter ones, argon and helium, is still at an early stage, while a neon compound is yet to be identified.